Welcome to AI Paper Slop, the series where we summarize AI and tech papers for technical folks who need to stay on the cutting edge. I mean, we don't do fluffy banter here, so let's just get straight into it. Today we're looking at a paper called Boogu-Image-0.1, Boosting Open Source Unified Multimodal Understanding and Generation.
Yeah, and this one is, it's a big deal. The core insights here should really make any ML engineer completely rethink their training pipelines.
Right, because this isn't just another incremental update.
Exactly. So Boogu-Image-0.1 is an open source model family that doesn't just compete with proprietary giants like GPT-Image-2 and Nano Pro, it actually matches or beats them. And the kicker is they trained the base model from scratch for only about $400,000.
Wait, $400K? That's like incredibly cheap for a frontier level model.
It is. And they did it using just 2 million unique images.
Yeah.
So they didn't just brute force the scale. They relied on Agentic inference time scaling, a highly curated data pipeline they call the Boogu Syllabus, and basically treating semantic understanding as a first-class architectural component.
I mean, that budget constraint is just wild when you consider the output. So to understand how a model trained on a shoestring budget competes with these massive frontier models, we really have to look at their fundamental philosophy shift.
Right, because they're moving completely away from standard text-to-image mapping.
Exactly. They see passive text-to-image as a dead end. Instead, they're moving to this active, understanding-driven pipeline that they call requirement-to-image.
Yeah, and that distinction is so critical. Users aren't just typing, a cat sitting on a couch anymore. They're passing in these complex, multi-layered intentions with implicit spatial constraints and stylistic rules.
So to handle that, the authors basically view the text encoder as the literal sensor of the model. I like to think of it like a self-driving car. If the car has a cheap, low-resolution camera, the driving algorithm is going to fail no matter how smart it is.
That's a great analogy.
Yeah.
It's the exact same principle here. If your text encoder drops the semantic nuance of the prompt, the diffusion model just generates garbage.
Right.
So they utilize Qwen3VL8B because they found that stronger LLMs yield massively better text encoding capabilities. Scaling up that reasoning engine anchors the entire downstream process.
So they bolt this highly capable reasoning engine onto the front end just to perceive the prompt correctly. But then the generation itself relies on agentic image generation at inference time.
Yeah, they don't just hand a vague prompt over to the diffusion model and hope for the best. Yeah. An agent orchestrates the whole thing.
And that starts with agentic prompt rewriting, which to me is basically like a master architect.
Oh, totally.
Like a client walks into an office and says, I want a nice house. That's a terrible, vague prompt. The architect translates that into a highly specific blueprint, detailing load-bearing walls, electrical layouts, materials. And then they hand that rewritten blueprint to the builder, which is the diffusion model.
And that removes the ambiguity that usually causes diffusion models to hallucinate. The paper actually has this great visualization of it. A user puts in something super abstract, like Newton's laws.
Which could mean anything visually.
Right, it's just a concept.
Yeah.
But the agent intercepts it and rewrites it into a highly structured typographical blueprint. It asks for a dark navy chalkboard background, 3 vertical sections, labeled force arrows with specific hex codes, and overhead museum lighting.
Oh, wow. So it's doing heavy prompt engineering automatically.
Exactly. And the agentic orchestration doesn't stop there. They also use model routing to manage compute costs.
How does that work?
The router is like a traffic controller. If a prompt has complex logical constraints or dense text rendering, it sends it to a heavy turbo model. If it's a simple stylistic thing, it goes to a much cheaper base model.
Saving massive inference costs in the process.
Yeah, and they even include a reflection step, so the agent can self-correct if the diffusion model misses a constraint during generation.
Okay, but wait. If this model prioritizes these hyper-specific, multi-layered instructions, rather than just drawing a pretty picture, how do you even evaluate that? Because standard benchmarks aren't looking for adherence to a massive design document.
They really aren't. And that's why the authors point out a massive flaw in academic benchmarks like Jan-Eval and DPG-Bench. They argue these benchmarks are just completely broken now.
Because they're saturated.
Saturated, highly prone to data leakage because they've been scraped into everyone's training sets. And most importantly, they don't correlate with human preference anymore.
Yeah, the data inversion on the leaderboards right now is glaring. If you look at GPT-Image-2, it absolutely dominates blind human preference platforms like El Marina.
Right, people just love its outputs.
But then if you run GPT-Image-2 through Jan-Eval, it only ranks mid-pack. which makes no sense.
Exactly. So to fix this, the team built their own testing ground called Boogu-Arena. It's a blind, pairwise ELO testing framework that actually mirrors real-world conditions.
What kind of prompts are they using for that?
They curated 1,200 bilingual prompts of varying lengths, but the key is they span 27 different user personas, everything from a casual novice to a professional UI/UX designer.
And on Boogu Arena, the Boogu-Image-0.1 turbo thinking variant basically dominates the open source tier. It even closes the gap with closed source frontier models.
Especially on prompt-sensitive tasks like text rendering.
But let me push back on this for a second. By abandoning standard academic benchmarks like Geneval in favor of an internal human preference arena, aren't we just moving the goalposts? Like, how do we ensure we aren't just optimizing for vibes over actual compositional accuracy?
That is a totally fair question. Because optimizing for aesthetic saturation is a huge trap in generative AI. But Boogu Arena avoids this because of those 27 personas.
Right, the professional persona.
Exactly. When humans do the blind voting, they aren't just saying, oh, this is a pretty sunset.
Yeah.
If the prompt comes from the graphic designer persona, it has rigid constraints on typography alignment, kerning, stroke structure.
Oh, so they're actively grading on strict obedience.
Yes. They're explicitly judging if the model obeyed those intricate structural rules. The turbo thinking variant wins because its agentic reasoning forces the diffusion model to respect the logic, not just output a hallucinated pretty image.
Okay, that makes sense. But to even understand concepts like kerning or isometric projection, it can't just be learning from messy web scrapes. The training data has to be radically different.
And that's where we get to the Boogu syllabus. This is how they won with only 208 million images. They argue that pure text-to-image generation is a dimensionality expansion task.
Meaning you take a low-dimensional text string and mathematically expand it into a highly complex, high-dimensional pixel matrix.
Exactly. And because of that massive expansion, you need significantly stricter data quality than standard visual understanding tasks. You can't just throw raw scale at it.
So they didn't just scrape the internet.
No, they built the syllabus based on human priors and logic. They ensured they had comprehensive coverage of fine-grained domains, like specialized graphic design and typography, things that standard scrapes completely miss.
The craziest part of their data curation to me, though, is how they handled the bad data.
Oh, yeah.
Normally, if you're making a pristine data set, you throw away images with watermarks, motion blur, or heavy noise. But they didn't. They kept them.
They kept them, but they explicitly captioned the defects.
Right. So by labeling a photo with heavy motion blur, they actually taught the model the mathematical concept of that artifact.
Which leads to highly controllable generation. If you don't want a watermark, the model knows the exact latent representation to avoid. But if you want a cinematic shot and ask for realistic ISO camera noise, it can reproduce it on demand.
Because it understands camera noise as a distinct variable, not just a random error. But speaking of concepts being baked in, I have a question about the cultural bias finding in the paper.
Yeah, that was a fascinating section.
The authors noted that Western-centric biases persisted even after they applied supervised fine-tuning, or SFT, with high-quality Chinese datasets. Why do foundational worldviews established in pre-training seem immune to downstream fine-tuning?
It really comes down to the geometry of the model's latent space. Open source pre-training data is overwhelmingly Western-centric, and that pre-training phase processes hundreds of millions of images over thousands of GPU hours.
Right. It's the bulk of the compute.
So it carves these deep foundational canyons into the latent representation space.
Mm.
When you do SFT later, you're using a much smaller data set and a lower learning rate. You're basically just adding a thin layer of topsoil over those deep canyons.
You aren't fundamentally rewriting the geometric association.
Exactly. SFT just lacks the mathematical momentum to override the pre-training distribution. So when the model gets an ambiguous prompt, it defaults to the deepest canyons.
Wow. So the foundation you pour on day one is just permanent. But okay, having the perfect syllabus is only half the battle. They still had to build an architecture capable of processing this deep semantic data without blowing up that $400K budget.
Yeah, and historically, you just slap a massive 72 billion parameter vision language model directly onto a diffusion transformer at DIT, but that is prohibitively expensive to run backpropagation on.
So they decoupled the architecture.
Right. They use a 32 billion parameter VLM as an instruction reasoner. It adjusts the logic, then passes a distilled representation to an 8 billion parameter instruction encoder.
And that encoder is what finally drives the 10 billion parameter DIT to make the image.
Exactly, it's a relay race. But even with that decoupled setup, they hit a massive roadblock when they tried natively training at 2K resolution.
Ah, right. The logit normal dynamic time shifting issue. Let's break that down, because this gets deep into the math. Standard practice is to adjust the noise schedule based on the image resolution.
Because higher resolutions have way more tokens. If you have more tokens, global coherence is much harder to establish at standard noise levels.
So dynamic time shifting pushes the noise schedule toward the higher noise regime, so the model learns the macro structure first.
Yeah. The shift factor scales linearly with resolution. But at 2K resolution, this linear extrapolation caused what the paper calls an oak squeezing effect.
Basically, it pushed the time steps so far toward the low noise regime that the median time step collapsed to near zero, right? It hit like 0.04.
Exactly. It completely degraded the signal-to-noise ratio. The model was spending all its time looking at nearly clean images, trying to denoise imperceptible static. Training convergence just stalled.
Okay, so their math-heavy solution was rectified dynamic time shifting, where they clamped the effective token count at 4096, which is the 1K regime.
Right.
But if you are artificially clamping the token count at 1K, aren't you essentially lying to the model about the true resolution? Like, why does freezing that scaling factor solve the noise problem instead of just creating new blind spots at 2K?
You're not really lying to the model. You're just preventing a linear extrapolation from destroying the noise distribution. Think of it like zooming out on a digital map to see the highways.
Oh?
If you zoom out based on a strictly linear formula, eventually the whole city shrinks into a single pixel and you lose all structural context.
Oh, I see.
The linear shift was meant to give a wider view. But at 2K, assuming that linear relationship holds to infinity, breaks down. By clamping the token count at 1K, they freeze the zoom level right before the model loses its bearings.
So it inherits a well-tuned noise schedule that still provides high noise computation, but stops the median time step from collapsing.
Exactly. It rescued the training dynamics beautifully.
The engineering discipline there is just wild. But even with the perfect architecture and training, generating the final image requires heavy steering at inference time. And historically, that steering introduces ugly artifacts unless you rethink the math of the guidance itself.
Right. You're talking about classifier-free guidance, or CFG. It's great for strict prompt adherence, but it's notorious for causing oversaturation, flattened tones, and that oversmooth plastic look at high scales.
Because the vector magnitude just explodes.
Exactly. So Boogu introduces a zero-shot training-free fix called Boosted Orthogonal Guidance, or BOG.
BOG, got it.
Yeah.
How does that rethink the math?
Well, first, it treats the predicted tensors as spatial matrices. It uses a rolling sum momentum to smooth the trajectory and normalizes the matrix to preserve spatial rank. But the real magic is the orthogonal decomposition.
Okay, unpack that, because a guidance vector has two parts, right? The orthogonal part, which is the semantic direction pushing toward the prompt, and the parallel projection, which is the magnitude of the existing noise.
Yes, and standard CFG just multiplies everything. So those parallel projections compound step after step, blowing out the image. BOG isolates the orthogonal components and boosts only those.
Effectively neutralizing the parallel projections from blowing out the saturation.
Exactly.
It honestly sounds exactly like high-end active noise-canceling headphones.
Oh, that's a good way to put it.
Like standard CFG is just cranking up the volume on your music to drown out background noise until the track is completely distorted and clipping. But BOG is like active noise cancellation. It mathematically isolates and neutralizes the specific interfering frequencies while keeping the original track crisp and perfectly balanced.
It's an incredibly elegant solution to a problem we've just been tolerating for years.
It really synthesizes all these technical triumphs of Boogu-Image-0.1. And I think what it means for anyone listening who's building their own ML projects is huge.
Absolutely. Open source development isn't just about hoarding GPUs anymore. It's about optimizing every single mathematical bottleneck.
Yeah, and before we wrap up, I want to leave you with a final lingering thought based on the paper's findings about cultural bias and data curation.
The pre-training stuff.
Right. The Boogu team found that cultural and conceptual biases baked into the massive pre-training phase cannot be overwritten by high-quality SFT later. So does this mean pre-training is destiny?
It's a heavy question.
It is. Because for AI researchers and ML engineers listening, this implies that you can't just indiscriminately scrape the web now and promise stakeholders you'll just align it later. It challenges the entire community to radically rethink early-stage data curation, knowing that the foundation you build on day one is permanently etched into the model's latent space. Think about how that impacts your own data pipelines the next time you kick off a training run.